In our series on linked list, so far we have implemented some of the basic operations like insertion, deletion, and traversal. Now in this lesson we will write code to traverse and print the elements of a linked list using recursion. A prerequisite for this lesson is that you should understand recursion as a programming concept. Recursive traversal of linked list actually helps us solve a couple of interesting problems, but in this lesson we will keep it simple. We will just traverse and print all the elements in linked list using recursion, and we will write one simple variation to print all the elements in reversed order using recursion. We will actually not reverse the list, we will just print the elements in reversed order. So once again I have taken example of a linked list of integers here. We have 4 nodes. Each rectangle here is a node. It has 2 fields, one to store the data and another to store the address of the next node. Let's say we have 4 nodes at addresses 100, 200, 150 and 250 respectively. And of course we will also have a variable that will store the address of the head node. Let's name this variable head. Programmatically in our C or C++ program, a node will be defined something like this. We will have a structure with 2 fields, one to store the data and another to store the address of the next node. What we want to do in this particular lesson is that we want to write 2 functions. First we want to write a function named print that will take address of a node as argument. We will pass this function the address of the head node, so let's name this argument head, and in this function we will use recursion to print the elements in the list. So for this particular example here, if we want to print a space separated list of all the elements, our output will be something like this. And we also want to write another function named reverse print. Here also we will take the address of a node, so we will pass this guy the address of the head node, and in this function we will use recursion to print the elements in the list in reversed order. So if we have to print a space separated list for this example, our output will be something like this. So let's first implement the print function. In my C code here, I'll declare print function like this. It will take as argument the address of a node, so the argument is of type pointer to node. Initially we will pass the address of the head node. We can name this argument head, or we can name this argument P. We can name it whatever, but we must understand that this will be a local variable. And let's not bother about other infrastructure in the code, like how we would create a linked list and how we would insert a node in the linked list. Let's assume that they are in place. So let's keep the name of this particular argument P. Now recursion is a function calling itself. So we have been passed the address of a node, initially the head node. So what we can do in our code is, first we can print the value at that particular node with a printf statement like this, and then we can make another call to the print function, and this time we will pass the address of the next node with a statement like this. This next field is also a pointer to node, so this will pass the address of this will be the address of the next node. There is one more important thing in recursion that we should never forget, and it's the exit condition from recursion. We should not go on making recursive calls infinitely. So in this case, if we go from the first node to the second node and from the second node to the third node using recursion, then finally at one stage P will be equal to null in one of the calls. At this stage we can avoid making a recursive call. We will exit. We will show you a simulation of how things will happen in memory. Hold on for a while. So once we will reach the end of the list, P will be equal to null, and we will exit the recursion at that stage. Now I'll write the main method. I've already written the insert function here, so I'll declare a variable head as null in the main method. So head will be a local variable. Once again we could name this particular variable A or B or whatever. Just because this variable points to the head node or the first node in the list, we name this variable as head, and then we will insert some nodes in the linked list by making call to the insert function that takes the address of the head node as argument. Initially head is set as null to say that the list is empty, and there should be 2 arguments to head. The to the function insert, the address of the head node, and the value that needs to be inserted. And why is it that this particular function insert is returning a pointer? It's because this head in the main method is a local variable, and if we pass it to the function, we just pass a copy of the address of the head node in this head, which will be a local variable of insert function. So this guy returns back the address of the modified head, so we can update it in the main function. This function inserts a node at the end of the list. So initially when head is null, head will be modified in the insert function. For other cases it will not be modified if we are inserting at the end. So we will make 4 such calls to the insert function to create a linked list of 4 integers 2, 4, 6, 5. And now we will make a call to print function and pass it the address of the head node. Let us now run this code and see what happens. As you can see, we have got this output 2, 4, 6, 5. The print function here in our code, which is a recursive implementation to print the lists, is working. Now I'll make one slight change in the print function. Instead of printing the value in the node and then making a recursive call, I'll first make a recursive call, and then when the recursive call finishes, I'll print the value in the node. And I'll not modify anything else in the code. The main method will remain the same. And if we run this code, we can see that the elements in the list are printed in reversed order. So we just implemented the reverse print function that we had talked about. Let us now analyze these two recursive implementations in a logical view. In our example here, if we want to print this particular list, we will do something like, from the main method we will make a call to the print function, passing it the address of the head node. So initially this print function is being called with p equal 100. Now in the execution of this function, we will come here if p is equal to null. Null is address 0 and our argument is 100, so control will not go inside this if condition. We will come here. We will print p arrow data. P arrow data means that we will first dereference the address. So we will go to the address 100 and then we will look at the data field there. So on the console we will print the data field of data field at address 100, and now we will make a recursive call. We will make a call to print function, passing it address p arrow next, which is 200. And the execution of this particular call will not finish. It will finish only after print 200 finishes. We will come back to it. Now print 200 once again prints the data at address 200 and then makes a recursive call to print function passing address 150, and we will go on like this. In this call to print with address 250, we will first print the data, and the address field, the value of p dot next, p arrow next, is 0, what we can also say null, so we will make a call like this. Now for this call with argument null, we have reached the exit condition. Recursion will not grow any further, so we will just print an end of line and return. This particular structure that we have drawn here is called recursion tree. So print null function call will finish and control will return back to print 250. There is no statement after this particular recursive call finishes, so we will simply exit this function call also, and control will return back to print 150, and we will go on like this. Finally we will come back to the main method. If you want to see how the recursion will execute in the memory, then I'll have to draw a diagram like this. Application's memory, the memory that is allocated for the execution of a program, has these two sections. All the details of function call execution and the local variables, they are stored in the stack section of the memory, and any memory that is allocated using the malloc function or the new operator in C++, they go into the heap section. The memory for the nodes in a linked list is allocated from the heap, so that's why these 4 nodes in our example are sitting in the heap. If you want to know in detail about stack and heap, check the description of this video for a lesson on dynamic memory allocation. When the program will start executing, first the main function will be invoked. Anytime a function is invoked, some amount of memory from the stack is allocated for the execution of that particular function. It's called the stack frame of that function. So let's say main is executing. We have already inserted some nodes in the linked list. We have this variable head in the main function. So all the local variables sit in the stack frame of the function. So head will sit here. Now at this stage, let's say main makes a call to print function. So main was executing and now it makes a call to print function. Execution of main will be paused and we will go on to execute the print function. The argument passed to the print function is 100, which is stored in a local variable. This argument p is a local variable in the print function. Now print function again makes a recursive call. Now stack frame is always allocated corresponding to each call of a function. So a function calling itself is not different from a function calling another function. At any time, whatever function call is at the top of the stack is executing. Finally, when we will reach the exit condition of the recursion, stack will be something like this. And then first this call where p is 0 will finish. We will come back to this particular call and then this will finish. And we will go on like this. So this is how recursion works. This is how things will happen in the memory. Okay, so now I'll clear this diagram of stack and heap in the right and I'll make some change in my print function. What I've done is I have renamed my function print as reverse print, and in my function I'm first making a recursive call, and after coming back from that recursive call I'm writing a print statement. And from the main function I'll make a call to reverse print. Let's write rp as shortcut for reverse print, and initially I'll pass the address of the head node. So I'll make a call like this, reverse print 100. The control will come inside this function. P is 100, it is not equal to null, and I've also drawn the console like before. Now this particular function call does not print first, it first makes a recursive call. So this guy will go ahead and make a recursive call to the reverse print function, passing it address 200. Nothing will be written on the console, and once again this particular function will make a recursive call like this, and once again this particular function will go ahead and make a recursive call like this, and finally we will have a recursive call where the function is passed address null. At this stage we will come to the exit condition in the recursion. The recursion will not grow any further. We will simply return, the control will return to this particular call, reverse print 250. So we will come here now to this printf statement. The data field at address 250 is 4, so 4 will be printed on the console, and now this particular function call will finish and we will go to reverse print 150. And now this call will print 5 and exit, and we will go on like this. Finally we will return back to the main function with this output on the console, the elements of the list printed in reversed order. So this was recursive traversal of linked list to print its elements. I must point out here that for normal traversal of the linked list, not for the reverse print, for the normal print, an iterative approach will be a lot more efficient than the recursive approach, because in iterative approach we will just use one temporary variable, while in recursion we will use space in the stack section of the memory for so many function calls. So there is implicit use of memory there. For reverse print operation we will anyway have to store elements in some structure, so if we use recursion it's still okay. In the coming lessons we will solve more problems, more interesting problems on linked list. So thanks for watching.